Okay, today we are just getting into the last little section of our trig unit, and then trig will be done. You guys will have it under your belt. We've got 2 applications lessons, so this is the first of 2. And then you guys are actually so close to finishing the course. We just have the 1 more unit after this. So that's great. Like, you should give yourself a pat on the back. You're almost through the course at this point. Our last unit, let me just pause this video quickly. Okay, so before we do some applications, I just want to look back at our little applet that we looked at a few days ago, just to make sure that we all kind of understand what the sine and cosine functions are tracking. This is really important for just kind of like grounding us in what the sine and cosine functions track so that we can extend that knowledge to our application questions. So the sine function, you'll notice, starts at 0, 0. So I'm looking at the wave graph right now, just over here. So when we look at the sine function, if you remember back to our last chapter, we said that we have a way of setting up the trig ratios in terms of x, y, and r, where x and y are a point on the outside of our unit circle, and r is the radius of the circle. And we know that for the unit circle, the radius is actually equal to 1. That's the definition of unit circle. So when we had our sine value and it ended up being opposite over hypotenuse, the opposite in this like little circle that we set up was y over r. And when we talk about the unit circle's radius is actually equal to 1. So what we actually get for sine is y over 1, which gives us simply the y. We're interested in the y for sine, not like literally the letter y, not W-H-Y. For cosine, we get adjacent over hypotenuse, which is x over r when we set up our x, y, and r. Do not know what my computer's doing right now. And cosine, when we do x, y, and r, and we set that up, and we plug in our unit circle radius, which we said was 1, we actually get x over 1. So cosine is actually tracking the x, okay? So cosine tracks the x, sine tracks the y of this point right here as we move around this circle with radius 1, okay? So I'm on the sine function right now. You can see in my selection over on the right-hand side here. The sine function tracks, we said, the y, because it was y over r and radius was 1. So what is the y coordinate at this point right here? Bonnie? 0, which is why we're at 0, 0 here. Okay, what's the y coordinate when we rotate up 90 degrees? 1. What's the y coordinate at 180? 0. And at 270? -1. And at 360? 0. Okay, so that is what sine is tracking. And if I switch over to the cosine graph here, we'll see that cosine is tracking the x coordinates of all of those points as we rotate that point around the circle. So what is the x coordinate at this location here? 1, which is why we're at 0, 1 here. And then what's the x coordinate at 90? 0 here. And at 180? -1. 270? 0. And 360 back over to 1. Great. So important thing to remember is sine is tracking the vertical or the y coordinate and cosine is tracking the horizontal or the x coordinate. Who wants to see tangent? It's burning in your minds. It's been keeping you up at night, I'm sure. No, this is tangent. It's pretty crazy.
We don't need to know that, right?
No, you don't. We're going to do it. We do that in advanced functions. Okay.
Is it hard?
No.
Then why is it advanced functions not advanced?
It's just advanced. It's not hard, Natalie. Okay, so that is kind of our big takeaway here, is that the sine function is tracking what we call vertical displacement of our point as it rotates around a circular object, let's say. So because the sine tracks the y coordinate, it tracks y because sine of theta, we know from last chapter, is y over r. And if we talk about the unit circle, the radius is actually equal to 1. So the sine is actually equal to that y coordinate when we talk about the unit circle. So if we have unit circle where radius, oh, definitely just spelled circle wrong. It's Friday. Circle. That tells us that radius is actually equal to 1. So what happens is we get sine theta is actually equal to y over 1, which gives us y. So we kind of consider, when I think about tracking something with a sine function, I want to think vertical displacement. Okay? I think about the up and down of the point rather than the left and right of the point. So we want to think, when we see sine function, we want to think vertical displacement. Okay, so we track the up and down of the point from the x-axis. All right, the cosine function, it tracks x because we know from last chapter that cos of theta is actually equal to x over r. And when we have our unit circle, which has that radius of 1, that means that the cos of theta will actually end up being x over 1, which gives us x. So when we think cosine function, we want to think horizontal displacement. Thanks, Liam. Okay, so we think about the left and the right of that point with respect to the y-axis. Katie.
Is horizontal displacement the same as phase shift?
Good question. So when we think about phase shift, it's talking about the shift of the wave function. So that is slightly different than this horizontal displacement that we're tracking, because we're actually talking about kind of more like that cast grid.
Okay.
So we're talking about the horizontal displacement of the point on that cast grid with respect to the y-axis. So we're actually talking about like our circular value like so. And when I think about the cosine function, I'm interested in how far the point is to the right or the left of this line. So as the point rotates around like so. So we kind of track its distance, and then that's how we create our curve. It will make more sense once we actually do a question. Yeah, but good question. So horizontal displacement is different than phase shift. Natalie?
How did you know all this stuff?
I did go to university for this. I've taught this course many times.
How do you just know, oh, this means this, when they all look the same?
I don't know. Just talented, I guess.
So,
Kylie's.
On like the cosine graph, wasn't it like the x thing on the circle thing
Yeah.
matched with the y on the graph? Like when x
Yes. So when we graph it, the horizontal displacement that we track is actually, so the x's are the angles, and the horizontal displacement that we track for cosine is actually the y coordinate that we plot on the wave function for cosine. Yeah. So I know that that's a little bit confusing, but hopefully these next couple of questions will kind of help you understand like what I mean by that. But yeah. Okay. So I'm going to show you a question just so we can kind of like understand what I mean by like vertical displacement and horizontal displacement. So let's suppose we are in the car of a Ferris wheel and we are in a Ferris wheel and its radius is 8 meters. It's turning counterclockwise. We're going to let the origin be the center of the wheel. So we're going to imagine that this point right here is actually the very center of where this wheel rotates around. And we're going to begin the sketch when the radius from the center of the wheel is along the positive x-axis. So the location of our car is actually going to be starting right here for where we track our vertical displacement. So if radius is 8 meters, this is no longer a unit circle. It's actually scaled up by a factor of 8. So I would like to actually just make a circle as best I can that actually has a radius of 8 on my graph. So I want it to go all the way up to the 8th unit here, which I think is here on my graph. If I counted correctly, 1, 2, 3, 4, 5, 6, 7, 8. Perfect. Okay, so this is 8, 8, negative 8, and negative 8.
Wow, that's a
I have a tool, a circle tool. But yes, that would have been impressive if I did that freehand. Okay, and then our starting position, the question tells us, is this location right here. So that's going to be our start. So our job is actually just to create the graph of the function that tracks the vertical displacement of our point, or of our cart, our Ferris wheel cart, as it goes around the circle here. Okay? So here, when we do applications, we partially throw our usual angles out the window in a sense, because wherever we start is 0 degrees. Okay? How far have you traveled when you're at the start?
0.
You've traveled 0 degrees. So wherever you start is actually going to be where the new 0 is. Okay? And you'll notice that if I don't start at the normal 0 degrees, that my graph down here will actually be shifted because I'm starting somewhere else. So here we're actually starting at the usual 0 degree line, and that just so happens to also be our 0 degree start. When we think vertical displacement, we want to think we're tracking the y coordinate. So at this location for our start here, what is the y coordinate? What is it? 0. So 0 degrees, we have a vertical displacement of 0. We're not above or below the x-axis at all. We're on the x-axis. Agreed?
Or aren't we on 8?
So that's horizontal displacement. So you're thinking left and right. This is actually the point. Maybe I'll actually write out the points for you guys. This is the point 8, 0. So the y coordinate, what's that?
Isn't that the start?
Yeah, that's a start. So what I'm interested in is my start, my degrees will be my x, and for this one, because I'm tracking vertical displacement, my y coordinate at this point will actually be my vertical displacement over here. Okay? So this point right here is the point 0, 8, and then we have 8, 0, and then we have 0, negative 8. So I'm actually going to be interested as we rotate around in all of these, each of these y coordinates. Okay? And then my x's will be the angle locations of where my cart is heading. Okay? So we are rotating counterclockwise here, which means the next position that we rotate to of importance is up here. Okay? How far have I traveled now, degree-wise? I've traveled 90 degrees. And what is my vertical displacement or my y coordinate at the 90 degree location? 8. Yep. I'm 8 units above the x-axis now, or above the center of the Ferris wheel. I'm 8 meters above the center. Okay? Now, how far have I traveled from the start? if I rotate down to this point?
180.
180. And what's my vertical displacement? So am I above the center of the Ferris wheel or below the center of the Ferris wheel at all? I'm actually equal to the center of the Ferris wheel, so I am 0 as far as vertical displacement. Okay, and then next location, how far have we traveled now?
270.
Okay, and am I above or below the center at all? I'm below it. How many meters? Yeah, so I'm negative 8 meters, or below the center 8 meters. And my last position is actually the same as my starting position. So I've now rotated a full 360 around the Ferris wheel. So I've done one full rotation, and I'm back to a vertical displacement of 0. I'm actually equal with the center. I'm not above or below it at all. So 0. So this is actually what we're going to graph down here. So I need my graph to accommodate points from 0, 8, and negative 8. So maybe we'll go by 4s. Maybe this can be 4 and 8. And this can be negative 4 and negative 8. And then we're just going to plot our points. So we started at 0, 0. And then we went up to 90 and 8, 180 and 0, 270 and negative 8, and 360 and 0. Okay, so there's my graph. It looks very similar to our regular sine graph. What's the only difference between this and my regular sine graph? So my regular sine graph usually goes between -1 and 1. So what if I changed here? Like, what if we wanted to make an equation for this? What would my equation be now? Has the period changed, or has it been shifted at all? Like, what's been changed here? We've changed the amplitude of the graph, right? Mm-hmm. So what do we change our equation to? Instead of sine x, what is it? 8 sine x, yeah. So our a value has just changed. So it's a regular sine graph, but the amplitude has been multiplied by 8. Any questions for this one so far?
Do you reckon the rest is the thing?
What do you mean?
Equation?
This is the equation, that's it.
There's no like transformations or
The only one is that our amplitude has been multiplied by 8, or changed to 8. Yep. Because the period is still 360. The center of my graph is at 0, right? We can see this is a C value. And my rising midline is actually on 0. So that's usually the D value of sine. So that's also 0. Okay?
but can't it be cosine?
We could do it as cosine, but normally if we see vertical displacement, we usually want to think of that as a sine function rather than a cosine function. So I usually express vertical displacement in terms of sine x. Okay? Good question. But yes, technically we could express this as a cosine as well. Okay, let's try another one. So part B says we're going to sketch a graph of the horizontal displacement versus the angle of rotation for one complete rotation. And this time we're going to start at the bottom. So I'm going to draw another circle, still has a radius of 8 meters. Okay, so points around the outside are actually the same. This is the point 8, 0, 0, 8, negative 8, 0, and 0, negative 8. The starting position has actually changed. The start is now here. And remember, whenever we start, that is the degree value that we're starting with. So I'm not interested in this 270 marker here. Wherever I start is the starting position when we've rotated 0 degrees at that point. Okay, horizontal displacement, I'm going to think cosine, okay? And I want to think x coordinate. So I'm interested in the x coordinate at all of these locations. So these ones here, the 0, the 8, this 0, and the -8. And that will become my y coordinate of my function, and the degree value will be my x coordinate of my wave function. So at the start, like we said, we are at 0 degrees. Can somebody tell me what the horizontal displacement is at the start? Or, so that's vertical displacement. 0. Good. Okay, now we're still rotating counterclockwise. So we're going to move up to this position here. How far have I traveled now from 0 to here? How far was that? 90 degrees. Great. What's my horizontal displacement now? How far am I to the left or the right of the center? I'm 8 units to the right of the center of the Ferris wheel, right? So at 90 degrees, I am 8 units horizontally from the center. Okay, next location, we're going to rotate up to this location here. And now how far have I traveled from my start? 180. Great. And what is my horizontal displacement here? 0. Yep. Okay, next location, how far have I rotated now? 270. Awesome. Horizontal displacement? -8, yes. We are 8 units to the left of the center now. And back to our starting position. Now we've rotated a full 360, and we're back at 0. Okay, so these points look quite similar to what we just did on the other slide. Although because we tracked horizontal displacement, we're actually going to refer to this in terms of a cosine function. So our equation will be slightly different. So let's just plot our points here. We had 0, 0, 98, 180, 0, 270, -8, and 360, 0. Okay, so that's my rotation starting at the bottom and tracking horizontal displacement. So you'll notice that the starting position was different. And we're also tracking something completely different. We're tracking horizontal displacement instead of vertical. So my function here, we could call it like, let's say we called it like height at theta. You could call it like that. Sometimes people use function notation for that. You can still call it f at x, whatever, it doesn't matter. But whatever you feel is a good name for it. I'm just going to call it f at x, just because that's easy. Our amplitude is 8, as we said, but because we tracked horizontal displacement, we might instead express this as a cosine function. But if I want to express this as a cosine function, where is my max?
8.
Yes, I'm talking horizontally though. It's at 90 to the right. So how can I express this in here in the cosine function? What do I have to do? Yeah, x minus 90. And this happened because we altered the starting position. We took the starting position and we brought it 90 degrees before the usual 0 degrees. That's why our max is now 90 degrees away from our starting position. Okay? This location right here, the reason why the max is on 90 is because this location right here has the largest horizontal displacement. It has the maximum horizontal displacement of +8. So that's why our max is at that location. Okay? So this is how we would express our function. Okay? Can you technically express this as 8 sine x? Yes, technically that is the same function. But we indicate to someone that we're tracking horizontal displacement when we use cosine. So, any questions so far? Okay. Part C. Suppose the trip was started at the very bottom of the Ferris wheel. Sketch the graph of the vertical displacement versus the angle of rotation for one complete rotation. Okay, so instead of us tracking vertical displacement starting at the usual 0 position, it's saying we now want to start at the bottom, which is where we would normally get onto a Ferris wheel anyways, right? We're not getting onto the Ferris wheel at the side of the Ferris wheel. So we're acting as if like we're literally getting onto a Ferris wheel where we normally would, and we're tracking the vertical displacement above or below the center. So we're going to see the effect on our graph when we do that. So same deal, again, it's going to be 8s all around. Okay, and our start is actually the same as our last question. It says we start at the bottom, which means that this is our 0 degree right here. And we are tracking vertical displacement. So when I think about the function for this, I want to think a sine function. And sine tracks the up and down. So I'm actually interested in the y coordinates at these locations as we rotate around. Okay? So at our starting point, we're at 0. And what is the vertical displacement at that point right there? -8, yeah. We're 8 units below the center. So we can see that our points already are a little bit different than our previous points. Okay, now when I rotate up here, how far have we rotated? 90. And what is the vertical displacement from the center at that point? Are we above the center, below the center, or equal with? Bonnie? We're equal with, so what would be the displacement? 0, yeah. And we can see that here is 0 as well. So that makes sense. So this is 90 degrees here. Okay? Next location is going to be up at the top here. And that's a full 180 from where we started. What is our vertical displacement now from the center? 8, yeah. Okay, and then around to the next location. This is a full 270 from where we started. What's my vertical displacement? 0, or the y coordinate at that location is what we're interested in. And then last location here, we are back at 360, and we're -8, or 8 meters below the center of the Ferris wheel. Okay, so when we graph this guy, I'll have the same y scale on my x and y axis. And now we started at 0, -8. Then we went up to 90, 0. It was 188, 270, 0, and 360, -8. So this is actually what our new graph looks like here. So there's our graph. That's one cycle only. So here's the question. How do we express this now as a sine function? So for sine, yeah, Alex?
Sine x
Yeah.
minus 90.
Great. So how did you get x minus 90? Ah, okay. So the midline is actually at 0, and Alex is noting that the rising midline is actually 90 units to the right of the y-axis. So that's why we have this 90-degree shift to the right. Okay, the amplitude has also been changed from 1 to 8. It's awesome. Why did we use a sine function and not a cosine function, Alex? Can you explain that to us? Yeah. So when we think vertical displacement, we want to think sine function. And I should probably add just into this question as well, usually this will say from the center, because vertical displacement can also be tracked from the ground as well. So yeah, I should really be specifying from the center or from the ground. Okay, questions for this one? Does this make sense? Okay, let's do a couple more with a different scenario, because this has been the same scenario every single time. Nicole, a question, yeah.
Just without graphing it, how do you know whether it's like minus 90 or plus 90? Because just from how I would think, that's 0, and you're going to where it should be 270, shouldn't that be minus 90 instead of plus 90?
Right, so if I start my graph earlier though, you have to imagine that we're shifting, like I'm actually starting at a minimum, right? So this location, when we think vertical displacement, the lowest point is actually the minimum of the function, right? The minimum will come just before the rising midline, right? So if this is the minimum, this is actually always the location of the rising midline when we're talking about vertical displacement. That location right there, because this is the max, right? So if this is the max vertical displacement and this is the minimum vertical displacement, the rising midline is going from a minimum to a midline and then rising up into a max. So this location is your rising midline location. So we actually start, does that kind of make sense when we're thinking about that? Yeah, so when we think vertical displacement, this location will be our rising midline because it's right between, we're going from a min to up to a max at that location. Good question. Okay, different scenario. We're going to imagine a carousel this time, and it rotates at a constant speed. It has a diameter of 15 meters. A horse that is directly in line with the center horizontally rotates around 3 full times. Create a graph that models the horizontal distance, or displacement, we can say, from the center as the horse rotates around. Okay, so diameter. This is the full length of the carousel, right? So when I'm doing horizontal displacement, I'm actually interested in radius, right? Because I want to know how far left or right we are from that exact center value. So what's my radius if the diameter is 15 meters? Katie?
7.5.
Oops. Right. So when I graph, here, I'm actually going to make my circle about 7.5 units from the center on all sides, as best you can, of course. So it's going to be about, where's 7? About right there. Okay, so these locations right here will be 7.50, 0, 7.5, negative 7.50, and 0, negative 7.5. Okay, the question also tells us that a horse is directly in line with the center horizontally. So I actually, just based on the information that I'm told in this question, I actually have 2 options for where I can place this horse, unless it tells me on which side it's in line with the center horizontally. In line with the center horizontally means it could be here, or it could also be here, okay? Because it doesn't give me any more information, okay? So I'm going to pretend, just for the sake of our learning for today, I'm going to pretend that this is our start, okay? So this is going to be our 0 degrees. And we are tracking horizontal displacement, which tells me I'm interested in cosine, which tracks the x coordinates as we rotate around that circle. So I'm actually interested in all of these x coordinates as we rotate around. Okay, so we're going to do just like one cycle, and then once we have those points for that first cycle, we'll just repeat it on our graph after we're done. So at our starting point of 0 degrees, what is our horizontal displacement? Or in other words, I'm asking you, what is the x coordinate at our starting point? Joey?
7.5.
Negative 7.5, yeah. Great, so it's 7.5 units to the left of the center. Okay, I also technically need to know the direction of the rotation. So I'm just going to tell you that this is going to go counterclockwise, okay? So next position, we are rotating down here. We are now 90 degrees from where we started. And what is our horizontal displacement from the center here? 0. That's right. Okay, and then next location, we're now 180 from where we started. What is our horizontal displacement from the center? 7.5, you got it. Next location, we're at 270, and we can see the x-coordinate here is 0. So we have 270, 0. And then when we go back around to 360, 360 is the same as 0 because it's the same position. So when we go back around to 360, it will have the same negative 7.5 that we had for 0. And we are graphing 3 full rotations. So I want to do 0 to 360, and then I'll do that cycle again for 360 to 720, and then one more time again for 720 to 1080. Okay? So let's just say here, maybe we can go by, what do you think, 2, 4, 6, 8? Okay, thank you for that confirmation there. I was doubting myself, but. Okay, so 7 and negative 7 are about here, which means 7.5 is going to be halfway between that 7 marker and the 8. So that's actually what I'm interested in. So we said at 0 degrees, which is this location right here, 0, we were at negative 7.5. So that's actually this location right here. And then at 90, we were at 0. So this is our 90. At 180, we were at 7.5, so up here. 270, we were back down to 0. And 360, we're back down to where we started, which is 7.5. Negative 7.5. Okay? That is one cycle around the carousel. That's one rotation. This is asking us to graph 3 of them. So we're just going to extend the pattern. So if I extend the pattern, the next point that I go to is back up to 0. And then at 540, we're up at 7.5. Next point will be 0. And then back down to negative 7.5. Okay? And then I'm going to do this one more time for the third cycle. So every single time this horse goes around the carousel, it's hitting the same horizontal displacements as it goes around to these points, right? That's why we have, it's a constant speed and it's hitting the same points again and again and again. So it's just going to be the same pattern over and over. Okay, and then our last point here is 1080 down at negative 7.5. All right, so here we go. We'll do our best to make sure that this looks somewhat curved. And so on, if it continues rotating around. Okay. What could be a possible equation that would fit this function? Katie?
F of x equals negative 7.5.
That's interesting. So you're imagining that there was a flip, right? That the max got flipped down. So we actually can express this as negative 7.5 cos. That's an option because that takes care of the location of the max for us. We're just saying that the max got flipped down to negative 7.5. Or can someone tell us another possible equation for this? What if I put my amplitude as 7.5? What would I have to do for the max? Where's the max shift? Alex?
7.5 cos x minus 180.
Yeah, so if I want to do positive 7.5, actually don't have a lot of space here. I'll do it up at the top. If I want to express this as positive 7.5, I actually have to do a shift of 180 to the right. So it'd be x minus 180. Okay, or you can do the negative. That works too. Okay, and notice that horizontal displacement, the max horizontal displacement, because we're working with cosine here, the max horizontal displacement is actually here. And we can see that's 180 degrees from where we started. So this is the location of the max horizontal displacement. Okay, and that happens at 180. So that's where we get this shift of 180. Question or stretch? Okay. Okay, for the last one, are we doing okay out there? We're good to finish up the last one? Do we need a break? Yeah? Okay, quick 2-minute break and then we'll finish the last part. Our last example for today, we are going to do something a little bit different than we did in our other questions. So we're going to have our Ferris wheel with diameter 15 meters and it's 6 meters above ground level at its lowest point. We're going to assume the rider enters the car from a platform that is located 20 degrees before the car reaches its lowest point. Model the height of the rider above the ground, so not from the center this time. So we've been doing horizontal displacement from the center and vertical displacement from the center. Now we're modeling from the ground, vertical displacement from the ground. As a function, model the height of the rider above the ground as a sine function as they rotate around. Okay, we're going to make a little sketch first of what's happening, and then that will help us develop our graph. Okay, so here's our Ferris wheel. Our Ferris wheel is 6 meters above the ground. Okay, this is our ground level. This is actually, this location right here is going to be where we measure everything from. So I'm just going to do this in red, just so we know that's our measurement location for each of these locations. Okay, so what is the minimum height that a rider could be on this wheel? Yeah, so this is the minimum, and it's 6 meters. Okay, can somebody tell me what the maximum is? This location is the max. What's the highest a rider could be above the ground, Bonnie? 21 meters. The 15 meters of the diameter plus the 6 meters above the ground. Okay, and then I usually like to just quadrant this out here. The rider could also be at kind of halfway in between the middle and the max. So if I know this whole thing is 15, we know each of these little slices or each of these pieces is 7.5 meters. Agreed? Like the radius. So what is the middle height that a rider could be above the ground? What's the midline value? Bonnie? 13.5, that's right. Great. Okay, so at the minimum, they can be 6 meters above the ground. At the middle height, halfway between the max and min, they can be 13.5 meters from the ground. And at their maximum height, they're 21 meters above the ground. Now this is telling us that they are starting 20 degrees before the minimum. So this right here is 20 degrees. Okay, maybe I'll zoom in just a tiny bit here. Before the car reaches its lowest point. So this minimum is, of course, the lowest point. So if this is our start, this has to be 0 degrees. Start is always 0 degrees. Well, how far have you rotated when you first get on a Ferris wheel? 0, right? Yeah. Okay, so wherever you start, it's always going to be 0. Start is 0. Okay, so I think we can technically mathematically calculate this, but for our purposes right now, we're just going to say the start is slightly above 6. You guys agree? It might be between like 6 and 8, somewhere between 6 and 8. But because it's just before we hit the minimum, I can see that this is just slightly higher than 6 meters. So we're going to start just above 6 meters. And then I'm actually just going to be interested in the rotation as we move to the important points, the max, the middle, and the min. So at the minimum, when we rotate, how far does it take us to get to this location right here at the minimum? How many degrees? 20 degrees. So at 20 degrees, how high are we above the ground? 6 meters. So at 20 degrees, from the start, we're 6 meters above the ground. That's awesome. Okay, so this is 20 degrees. Next location, we're going to slide up to the middle location. How far have we rotated from the start now?
110.
How did you get that 110?
20 plus 90.
Yeah, so this is 90 right here, and that was 20. So if I do 20 and then a full 90, I'm at 110. And what is my height above the ground here? 13.5. Awesome. Okay, next location, how far am I from the starting point?
200 degrees.
Yep, so I'm adding another 90 on here, so this is 200 degrees from the start. And how high am I above the ground here?
120.
That's right. Okay, next location, how far are we now? 290. Okay, adding another 90-degree angle there. How far are we above the ground at 290? Yeah, we're halfway. Again, 13.5, awesome. And back to our starting position. How far have we rotated if we've rotated all the way around the Ferris wheel back to our starting position? 360. So at 360, we're back just above 6. Okay, again, we can calculate this mathematically. We can try to use Pythagorean theorem and all that nice stuff. But for now, I think that just above 6 is okay.
On the
Joey?
test, can we say just above 6?
So we're going to do just a really quick calculation to figure out this value right here. Okay, so off to the side, I just want to, excuse me, I'm just going to create this right angle triangle right here. If I create this right angle triangle, I know that this is 70 degrees right here. And I know the length of the radius. So if I can figure out this horizontal length right, or this vertical length right here, maybe we call that V. If I know the radius and I have a right angle triangle, I should be able to find that vertical length and then find the exact length above the ground. So I'm just going to do this off to the side. We had a 70-degree angle, and we are interested in this vertical height right here. And I know this is 7.5 meters because that's the radius, and this is 70. So this is opposite and hypotenuse, and we're just going to do a really quick SOHCAHTOA calculation here. Alex? So sine of 70 is opposite, which is V, over hypotenuse, and then we're going to calculate what that vertical height is. So just type that quickly into your calculators. We'll see what we get. Alex?
That's 7.04.
Okay. So this is actually the height from 13.5 to, it's the height from the middle to the bottom. I actually want the height from the ground. So again, just to remind you, if this was our circle, we had our triangle that we set up, like so. And this was 13.5 meters. So if this is 7.04, I'm actually interested in how far we are above the ground here. So how can I find this little height right here? If I know this whole thing is 13.5? Joey?
13.5 minus 7.04.
Great. Did you calculate that? What do we get there? If I subtract these, I should get the height above the ground. Alex?
6.46.
Great. So we were right in estimating just above 6, but now we know it's exactly 6.46. Okay, so if ever you need like a height that's not a max, a mid, or a min, you can always use Pythagorean theorem to help you out with that. So now we know our height that was just above 6 is actually 6.46. So we can actually enter that in here at 0 and at 360. Liam? Yep. Okay, so now all that's left for us to do is just draw a little sketch of our graph. So again, it's a rough sketch. I'm not interested in the negative part of this graph because I don't have any negative heights above the ground. So this is degrees and height above the ground. The highest we have to go is 21, so maybe we do 6, 8, 10, 12, 14, 16, 18, 20, 22. So I'm going to go by twos. So this will be 2, 4, 6, 8, 10, and this will be 20.
Is this still part of A?
Yep. Okay, and then over here we're going to go could go by 20s up to 360, or maybe could try 40s, or we could just do like the regular 90. So maybe we do like 45, 90, that would be 180, 270. So this will be 45, 135, 235, 225. And 315. Okay, so we're just going to kind of like approximate these points as we need to here. So our start, we said, was 6.4, just above 6, 6.46. And then at 20 degrees, we were down to 6. So 20 degrees is going to be like, I don't know, just under halfway for 45, because half of 45 is 22.5. So our 20 degrees will be just under the halfway point, right about here. And then our next point was 110, 13.5. So 110, just about here-ish. We're up at 13.5. Maybe just over slightly. Okay, 221. And then 290, 13.5. and 360 is back just above that starting point, or just above that minimum where that starting point is, at like 6.49 or 46, I think it was. So here's our full cycle. Goes like this. Alex, put your phone away. Okay, so what is this as a sine function? This is my question. So here's our midline. It was at 13.5. So that's actually our C value, 13.5. What's the amplitude of this function here? 7.5 is the amplitude. Just as a little hint to you, the radius of the object is always your amplitude. Is our period still 360, like the usual sine function? So is there any k value change? No, so k is the same. What about the location of the rising midline? That's this location right here, right? Where was that? 110, yeah. So I want to say 110 to the right, so I'll say x minus 110. And what about my C value here? I have to do this midline location. So I'm actually going to use that middle location of 13.5. Okay? For part B, it asks us to model this using a cosine function. The only thing I have to change for part B is that shift value. We'll still call it h at x. So what does my shift value change to when I express this as a cosine function? I don't even need to calculate it. I should know from looking at my points here. Where's the max? Alex? Yes, minus 200 is what the shift changes to. And that's just because our max is over here at 200. So this is D for cos. And this guy right here is D for sine. Okay, so that's part B. Nice and quick. Okay, I can tell from the picture where my rising midline value will be from this right here. That's the rising midline right there. And I can tell from my picture where my max will be. I don't even need to look at the graph. I know the max is at 200. So that should help us in developing our equations as well. Okay?